Okay, so let us look at value iteration, one of the dynamic programming based algorithms to compute the optimal value function and also the optimal policy for an MDP. So this is the update rule for value iteration, as you would recall from the lectures. So there are two ways of looking at it. One is to look at the Bellman optimality equations that you have here and turning it into an update rule. So how do we do that? The V star that is there on the right, we call that Vk, and the one on the left, we call that Vk plus 1, giving us the value iteration update rule. The other way is to see it as some form of policy iteration in which the policy evaluation step is truncated. So assume that you have some value function Vk at some stage in the algorithm, right? So if you behave greedily with respect to this Vk, then you will get a new policy pi. Okay, so this is the policy improvement step in policy iteration. What you do now is, instead of doing policy evaluation, the full-blown policy evaluation, you just do one round of updates. Okay, we call it V pi superscript 1 of s. This 1 stands for one round of policy evaluation. Okay, so some of you are wondering where that sigma over a pi of a given s has disappeared. That is actually implicitly contained here, okay, in this pi of s, right? So pi of s is the deterministic action in status, right? Pi is a deterministic policy. So this is actually one update of policy evaluation, right, for each state. Now this is nothing but max over a of this expression. Why is this? This is how pi of s was obtained, right? You did an argmax over a of this expression to get pi of s. Now you are substituting that same pi of s here, same Vk here. So this is nothing but max over a of the same expression. Okay. Now this is what? This is one round of policy evaluation. What you now do is you make this Vk plus 1 of s. Okay. Therefore, you end up with this update rule Vk plus 1 of s as max over a of this expression. Okay. So this is what? This is some kind of policy iteration you are doing, but instead of doing policy evaluation until your value function converges to V pi, you stop it after just one round, right? So it's a truncated policy evaluation that's happening here, right? Not just truncated policy evaluation, that's just to highlight what is being truncated, right? So the policy improvement step remains the same, but you don't do full-fledged policy evaluation, you truncate it after one round. So if you view it that way, you end up getting value iteration. Okay, this is another way of looking at value iteration. Now we looked at the MDP example, the manufacturing example in the lectures. We'll take up the same example and we look at how value iteration works for this case. So we have two states, hot, cold. Okay, from each of these states you could have two actions, advertise or not advertise. That is the set of possible actions from the state hot. The state cold, you could have two actions. You could either research or you could not research. Okay, so the transition probabilities and the expected immediate rewards are given on the edges. Okay, this is a simple transition graph that you must all be familiar with by now. Given this transition graph, what we will do next is we will go ahead and convert this into a tabular form, so that makes it easier for us to compute the value functions in the value iteration algorithm, right? That's what we will do next. So notice that we have two states and we are going to name them S1 and S2, hot and cold. And there are two actions, right? A1, A2. So A1 will correspond to the affirmative actions of advertising and researching. A2 will correspond to the negative actions of not advertising and not researching. Depending on the context, whether you are in state S1 or state S2, A1 will either be advertise or research. Likewise, depending on which state you are in, A2 will be not advertise or not research, right? So this will become clear based on which state you are in. So what is the table going to look like? It's going to look like this. If you are in state S, take action A and move to S prime. What is the probability of this transition? That is P of S prime given S comma A. And what is the expected immediate reward that you will get along the way? It is R of S A S prime. Okay, so the transition graph here has been converted into this tabular format that you see here. Okay, so we have completely specified the MDP now. We have the states, actions, transition probabilities and reward expectations, right? All these four together specify the MDP. Once we have this in place, what we have to do next is go ahead and compute or run the value iteration algorithm on this MDP. Before we go there, let's go back and take a look at the value iteration update rule. So what does it have here? It has the joint distribution of S prime and R given the current state and action. Okay, so that's what is there. But what we have tabulated here is the transition probabilities and the reward expectations. So one question that you might ask is, how do we move from this joint distribution to these transition probabilities and reward expectations? That's what we will do next. Okay, very briefly we look at this. So this is the equation for the action value function Q pi of S comma A. Right, so you have it in terms of the joint distribution P over S prime R given S comma A. So how do we move from here to the transition probabilities and reward expectations in terms of SA S prime? So it's quite simple. You have to break down this probability using the chain rule of probability. You have to break down this distribution into two parts, right? One is P of S prime given S comma A. Starting from state S, taking action A, you move to S prime. Once you are in S prime, this is the reward that you see. Okay, this is just a simple application of the chain rule of probability. Alright, now what you do is you break down this summation into sum over S prime, sum over R. After all, what is this? This is a joint sum, it's a double sum over S prime R, right? All possible values of S prime, all possible values of R. So you do that. Since this transition probability doesn't depend on R, that can be taken out of the summation over R. Okay, that can be taken out. And what we have here is summation over R into P of R given S prime S A. What is this? This is nothing but the expectation, right? This is nothing but the expectation, which we denote as R of S A S prime because it's a function of the current state, action and next state, right? So this is the reward expectation R of S A S prime. What is this quantity here? Notice that this summation over R also holds good for this gamma V pi of S prime P of R given S prime S A, right? So since gamma V pi of S prime is independent of R, that can move out and this will just become a summation over R P of R given S prime S A, and that summation will just be 1. Why is that 1? P of R given S prime S A is a probability distribution over R. So we are summing this probability distribution over its support, so that will be 1. That has to be 1. Okay, so if you do these two changes, you end up with summation over just S prime, P of S prime given S comma A into the reward expectation plus gamma V pi of S prime. Okay, it is this form of Q pi of S A that we'll plug into the value iteration update rule. Okay, so what we have now is the tabular form of the MDP on the left. What is the first step? We initialize the values to 0. Okay, we could initialize to any arbitrary value, but what we'll do is we'll initialize V of S1 and S2 to 0. 0 V naught or V subscript 0 is nothing but time step 0, right? And this is the update rule Vk plus 1 of S in terms of Vk. Now what do? We have to compute Vk plus 1 of S1. We'll come to this specific example that we have here. So what is Vk plus 1 of S1? It's a max over all possible actions that you can take in S1. How many actions can you take? 2 actions, A1 and A2. So first let's look at A1. Okay, let's look at A1. what is this expression we have here? It's a summation over all possible next states. What are the possible next states? You have two possible next states. Okay, so it becomes this summation over S1, S2. Okay, that's what the first term here is and the second term here is. This is the transition probability P of S1 given S1 comma A, right? So the top one is the following. It's if you are in state S1 and you take action A1, you go back to S1. That is what the top set of terms actually are looking at. The bottom set of terms are looking at starting from S1, taking action A1 and transitioning to S2, right? So this whole thing, if you sum them, you will get this summation that we have here. This is for one action A1, right? That's why A1 you see all throughout. If you do something similar for A2, you will get this. Okay, notice that the only difference between the one on the top and the bottom is that the A1s have been replaced by A2s. Okay, so all this is the value for state S1 in time step k plus 1, how to compute it in terms of the values at time step k or iteration k. So do the same thing for S2. Okay, do the same thing for S2. Now keep doing this until you converge. Okay, where convergence you have a specific criterion. The difference between successive value function should be less than some theta. Okay, that is up to you to decide what the theta should be. Alright, now that we have the base setup, let's go ahead and run iteration 1. Okay, what is iteration 1? We start with V naught of S1 and V naught of S2 to be 0. So we have to compute V1 of S1. How do we compute V1 of S1? Okay, so we look at action A1 to begin with. So if you are in S1, you take action A1 and you transition back to S1. The probability of the transition is 0.8. Right? Along the way, you will get an expected reward of 4. And you are now transitioning back to S1, right? So the value of that is 0 currently, right? Vk of S1 is 0. In this case, k is 0, right? So V0 of S1 is 0. So you have plus gamma into V0 of S1. Now this is one arm of or one possibility of the next state, right? You have to consider the other possibility, which is S2. So if you move to S2, then the probability is 0.2 and the reward expectation is 4. Gamma V of S2, right? V0 of S2, that is also 0. Okay, this is all for action A1. This is all for action A1. Now you have to do likewise for A2. Okay, you have to look at A2, S1, A2, S1, S1, A2, S2, what happens? Right? If you now compute this, you will get 4 and 6 respectively. Max of that is 6. Okay, so V1 of S1 is 6. You do the same thing for V1 of S2. Okay, instead of looking at the top part, the top half of this table, you look at the bottom half of the table. For state S2, everything else is a similar computation, right? The computation is similar. Okay, only thing is that the transition probabilities and reward expectations will change. Okay, the max here turns out to be -3. So the value at iteration 1 of state S2 is -3. Okay, so you started off with V0 of S1 equal to V0 of S2 equal to 0. You ended up with V1 of S1 equal to 6 and V1 of S2 equal to -3. This is iteration 1. Now iteration 2 is very similar. Okay, we will start off with 6 and -3 as the values. We will find out what V2 of S1 is. Notice that the transition probabilities and the reward expectations are going to stay put. Okay, gamma is equal to 0.9. That's one change. Okay, we have explicitly set gamma here. Earlier we didn't need the value of gamma because now what happens? You have to compute V2 of S1. So V1 of S1 is 6, V1 of S2 is -3. So we use those values. We end up with V2 of S1 to be 7.78. Likewise, you can compute V2 of S2. That turns out to be -2.03. Okay, you keep doing this until you reach iteration 57. In iteration 57, you have V57 of S1 to be 22.2 and V57 of S2 to be 12.3. Now, if you do V58, if you go for the 58th iteration, you see that V58 of S1 is also equal to 22.2 and V58 of S2 is 12.3. That is, there seems to be no change in the values from the previous iteration to the current iteration. Okay, so we can kind of reasonably say that our value function has converged. Okay, the small catch though is we are only looking at one decimal place, right? One decimal place after, or rather the precision is one decimal point, right? One place after the decimal point, right? So let me repeat that. Our precision is only one decimal place after the decimal point. Okay, so if you look at more decimal places, right, and if you have a more stringent tolerance, then we can't say that it has converged after 58 iterations. We'll have to go for more number of iterations. So if you do that, you will see that it converges after 73 iterations if the tolerance you set is 0.001 or 10 power minus 3. Right? If you look at the exact values, they turn out to be 22.190, 12.300, of course rounded off to 3 decimal places here, right? So we can stop at this stage and say that the value iteration algorithm has converged. Okay, but the question is, has it converged to the optimal value function for this MDP? It's a bit tricky, right? So all that we can say is that it is pretty close to the optimal value function. So V star of S1 and V star of S2 may not actually be 22.2 and 12.3. So all that we can claim is that they are pretty close. V star of the values that we have computed are reasonably close to V star of S1 and V star of S2. Okay, that's all we can say at this stage. What next? Now we can ask the question, okay, now that we have an estimate of V star, a reasonably good estimate of V star, what is my optimal policy going to be? So how do we compute the optimal policy? By behaving greedily with respect to our estimate for V star. Okay, so pi star of S is argmax over A, Q star of S comma A. This expression is nothing but Q star of S comma A. Okay, so let's go ahead and do that. Pi star of S1 will be argmax over this quantity. I have just computed this quantity. Instead of taking a max, earlier we were taking max. Now we are taking argmax because we need the policy, right? So argmax here is going to be A1. So the first one corresponds to A1, second one corresponds to A2, right? So what is the maximizing action? It is A1. If you do it for pi star of S2, you will get that also to be A1. You have to be careful here. Depending on the context, A1 differs, right? So pi star of S1 therefore is the affirmative action of advertising. Pi star of S2 is the affirmative action of research, right? So that's the optimal policy. Though, what does the optimal policy tell you to do? Whenever you are in the state hot, advertise. Whenever you are in the state cold, research, right? So seems like pretty good advice for this company. So this is the optimal policy that we have obtained using value iteration. So let's now go ahead and see how to implement this using code. So we'll import NumPy, and we'll now look at how to define the grid world. So there are two states, S1, S2, two actions A1, A2, and this is how we are going to define our transitions, right? So remember that the transition probability is a 3-valued function, S, A, S prime. So we'll do a triple nested dictionary. So S is the outermost dictionary key, A is the innermost dictionary's key, and the middle dictionary's key, and S next, or S prime, is the innermost dictionary's key. Okay, and we say that it's 0 to begin with. We initialize it to 0. We do something similar for the reward expectations, again a function of S, A, S prime. So it's a triple nesting here. So what are the transitions? Now we can go ahead and fill the transitions. So whatever is the tabular table here, S, A, S prime, we are just filling it up. Okay, so this is 0.8, 0.2, 0.5, okay, so on and so forth. Likewise, R of S, A, S prime, we are going to fill it up using these values. So you will see the resemblance between the table and the two dictionaries here. Okay, so that is the definition of the world. So we have specified the definition of the world. We also have to specify gamma equal to 0.9. Okay, so we treat this, by the way, we treat this as a continuing task, right? It's not episodic, but continuing. So what is the key equation This is the key equation. If you notice, this is actually some kind of a q value, right? So sigma over s prime p of s prime given as a into the expected reward plus gamma vk of s prime. So this is what we need to implement. So what is the code for value iteration? We have the parameters or the variables for convergence set here, theta, delta, and the number of iterations. We initialize it to 0. So what is our initial value going to be? It's going to be 0 for all states. Okay. So what is convergence? When the difference between successive value functions is less than theta, then we have converged. So when have we not converged? Whenever delta is greater than or equal to theta, that means we are not yet close enough. So we run one more round of value iteration. So update the value of iter and set q to be 0 for all state action pairs. Okay, set q to be 0 for all state action pairs. Now, one important point that I missed out mentioning while we were looking at the slides is that we are doing synchronous updates here. Okay, synchronous updates meaning we maintain two values or two copies of the value function, one for vk and one for vk plus 1. Okay, that's the one we'll be doing here. So v next or vk plus 1 is also set to 0. Okay, we set delta to be 0 for this round of value iteration, and internally we update delta, right? We update delta here. Now let's start, right? We have to compute, remember, we have to compute q of s comma a and then find out the maximum of q of s comma a for a given s and set that as the new value of vk plus 1, right? So v next of s will be, let's look at that first. V next of s will be what? It will be max of q of sa for a in a, right? So what we have to do now is compute q of sa. How do we do that? For each state in capital S and for each action a, we have to look at all possible next states, right? Once we do that, we compute the probability of this transition, that is p of s a s prime. P of s prime given s comma a is nothing but this quantity, and the expected immediate reward, which is r of s a s prime plus gamma v star of s next. S next is s prime, right? This is what is this? This is nothing but p of s prime given sa into r of sa s prime plus gamma vk of s prime, right? This is we have done it for one triple sa s prime. What we are doing here is we are doing it for all possible values of s prime and for all action a, right? For all action, for every action a, we are doing this for all possible s prime, right? So the summation over s prime is captured in this particular update, right? So the summation over s prime here is actually captured in this particular update. Okay, so once we come out of this inner loop, we will have q of s comma a. We have to keep doing this for each a. So once you come out of this loop, you will have q of sa for all a. Once you have q of sa for all a, you have to do what you have to do. So where is the equation? Let's go back. Let's go back to the value iteration update rule. So once you have computed this quantity here for all possible a's, you have to do max over this a, right? You have to find max of this. So that's what we are doing here. Max over a, q of s comma a, and you assign that maximum value to vk plus 1 of s. Okay. So once you have done this for one state, for the state s, you update delta, right? How close is my current value function v of s to the next iterations or next time steps value function for the state s. So you use that to update delta. Okay, now repeat the entire procedure for the next state s. Okay, keep doing this until you go through one complete sweep of the state space, right? So let me write that down here. One sweep of the state space, right? You do this for one complete sweep of the state space. That will complete one iteration of the algorithm that we call value iteration, right? So once you do all this, you would have completed one iteration of value iteration. Okay, at which stage you make sure that you update the current value function to this, right? So v next is your new value function. You make that the current value function v so that you can go ahead and do the same thing, repeat the same procedure for the next iteration of value iteration. Okay, so let's run this and see what happens. So we see that it converges after 73 iterations for the value of theta being 10 power minus 3. Okay, so let's now also print what the intermediate steps look like. Okay, what do the intermediate steps look like? So what am I printing here? I am printing the iteration number, the value in state S1 and the value in state S2 rounded off to 3 decimal places, correct to 3 decimal places. So let's compare this with what we computed. So we computed V1 of S1 to be 6 and V1 of S2 to be minus 3. That's what we have here, right? 6 and minus 3. Then it turned out to be 7.78 and minus 2.03, exactly what we have here. Now if you continue doing this, you see that V1 of S1 keeps on increasing, V2 of S2, V1 of S2, rather Vk of S1 and Vk of S2 both keep on increasing until you go somewhere near iteration 57. Okay, look at this, right? So we stopped at 57, 58 when we rounded off to 1 decimal place, right? So this is, if you round it off to 1 decimal place, this is nothing but 22.2 and 12.3. 58 is also 22.2, 12.3, right? So that's what happens. And of course, if you take more decimal places, like 3 decimal places here, you converge after 73 iterations, right? One point to keep in mind is that what we have here is synchronous updates, right? We have done synchronous updates by maintaining 2 separate copies of the value function, one for the current time step and one for the next time step. You could also do this in an asynchronous manner. How will you do that? You will just get rid of v next and you will just have one copy of the value function, right? That's an asynchronous update. So if you just retain one copy of the value function, that's an asynchronous update, right? So that's the end of this tutorial on value iteration. Thank you for watching.